In the icy and silent vastness of space, the stars seem apparently immortal and unchanging, yet some of them shine with a deceptive serenity. Because they are unstable, they are cosmic time bombs that carry within them a tragic destiny, that of collapsing under their own weight, before disappearing in a spectacle of fire, plasma, and light with a brightness comparable to that of billions of suns combined. As you've probably guessed, today we're going to be looking at the absolutely astonishing phenomena that are capable of literally pulverizing stars by turning them into supernovas. But before we dive into the excess of events that are among the most energetic in the universe, a few reminders about how stars work are in order. In broad strokes, stars only have two ways to die. They can explode or simply cool down, fading out more or less slowly. And to understand why, we must remember that all the stars in the universe operate in the same way. At the center of each one of them, the density and temperature of several million degrees allow the lightest element in the universe to fuse hydrogen, which they are primarily composed of, into helium, while releasing large amounts of energy in the form of radiation in the process, which prevents the star from collapsing on itself while making it shine. In other words, all the stars in the universe are in balance between the force of gravity that compresses its core, to the point of igniting nuclear fusion reactions there, and the energy released by these, which oppose their collapse. But the amount of matter that stars have in their core is limited, and when hydrogen starts to run out there, the amount of energy released decreases and gravity takes over. Compressing the center of the star, it increases the temperature and pressure to the point of initiating the fusion of the helium that has accumulated there. Almost all of the stars that populate the cosmos are not capable of going beyond this level of fusion. And as the helium is transformed into carbon in their core, these will slowly extinguish over dizzying lengths of time, far greater than the age of our universe. Currently, so much so that none of these stars has yet been observed dying. As for stars of the type of our Sun, when they attack helium, they are destabilized by the arrival of this new and powerful energy source and begin to swell, until helium in turn comes to be lacking in their heart, that the amount of energy released within it decreases and that it contracts and rises in temperature until initiating the fusion of a new element. To summarize, these stars continue fusing elements, climbing the fusion ladder until the process definitively ends. When unable to fuse new elements, they come to expel their veil of gas into space, slowly disintegrating, giving birth to a planetary nebula, a nebula at the center of which lies a white dwarf. A small core of bare stars, barely the size of our planet, and which, no longer being the seat of nuclear reaction, begins to slowly cool. These two types of endings, relatively peaceful, fade out over a small eternity or go poof. This is the fate that awaits all the stars in the universe, whose mass is less than 8 times that of our Sun, and which represent nearly 97% of the stars that populate the sky. And then there are the others, the gigantic ones, the two big ones, which will follow a very different tragic trajectory. Because, beyond a critical mass estimated to be 8 times that of our Sun, stars are destined to meet an end of incredible violence by turning into supernovas. If the heaviest stars always burn the candle at both ends, it's because, counterintuitively, the lifespan of stars is inscribed in their mass. And while the smallest of them can shine for hundreds, even thousands of billions of years, the most massive inevitably end up disappearing in a few million years, at most. Now that we've covered the basics, you can sit back and watch the final moments of existence of giant stars. Starting with the most common ones, the stars that die by core collapse. Let's take the typical example of a star with about 20 solar masses, like the smaller stars. Such a space monster begins its life shining, thanks to the energy released by the fusion of hydrogen in its core. And when it starts to run out, after just a few tens of millions of years, the giant star will start to climb the fusion ladder without anything seeming to be able to stop it. It swells and transforms helium into carbon, then carbon into neon, neon into oxygen, and oxygen into silicon. Each time a star's fuel is exhausted, its heart contracts, increasing in temperature and density. And in the process, it forges a new element which it then uses as fuel. So much so that the star develops an onion pot structure. in which it fuses increasingly heavier atomic elements at increasingly higher temperatures as one approaches the center. Until it goes wrong, because once the star starts synthesizing iron, hell starts to break loose. Because the arrival of this newcomer will tip the balance of the star into the unknown. Iron is the most stable element in the universe, which means that modifying its nuclear structure requires more energy than it releases. As a result, the star's core becomes saturated with this element that won't fuse without being able to eliminate it. And as it intoxicates itself with this kind of energy dead end, the core contracts further, with no additional energy released to oppose the process. A vicious cycle is launched. The center of the star quickly transforms into an extremely compacted iron ball, nearly 3,000 kilometers in diameter and heavy as 1.5 times our Sun. And then, by overloading with iron, the heart of the giant star comes to press the trigger. Because, by accumulating there, the metal ended up suffocating the heart of the star. In a now practically extinguished core, nuclear fusion reactions stop and suddenly, hell begins. The balance of forces is broken. The luminous power emanating from the center, like the degeneration pressure of electrons. The last bastion, preventing the heart of the star from collapsing on itself, are defeated, unable to counterbalance the force of gravity. In a few milliseconds, the deepest part of the star's heart collapses on itself and sees its volume compressed by a factor 1 million. The staggering gravity of the newly formed heart drags in its wake the peripheral layers of the star, which fall in its direction and hit its surface. At nearly 25% of the speed of light, the central star, now composed of virtually incompressible matter named neutronium, absorbs the violence of the shock by starting to oscillate. The surrounding space-time distorts, and in the wake of the impact, shock waves propagate in cascade, creating terrible turbulence. Most of the matter, which hit the core at nearly 1/4 of the speed of light, bounced off it, generating huge pressure waves that propagate through the star, compressing and heating the layers they encounter along their path. Practically at the same moment, a quantity of neutrinos carrying more energy than that emitted by 100 billion stars combined bursts from the central ball. These particles are born from the fusion of electrons and protons that occurred when the iron ball, nearly 3,000 kilometers in diameter, transformed into a sphere about 20 kilometers wide. The terrifying power of this neutrino flow, formed by the rearrangement of matter within a core that has become a small neutron star. It exerts such a phenomenal pressure in its progression towards the outside of the giant star that it reverses the collapse. Coupled with the violent shock waves that propagate through the overheated layers of the star, like an infernal snowplow would do, these particles will thus blow up the giant star from the inside, a giant star which, at the time of its explosion, is so vast that it takes a few dozens of minutes for the neutrino, which propagates from the center practically at the speed of light, to reach the surface. While the shock waves will take several hours to cross all the layers of the star before coming out by tearing it apart violently, it is at this moment that, for an outside observer, the star truly transforms into a supernova. A gigantic and apocalyptic eruption of matter and radiation that embraces the sky with an almost unreal light. For several weeks to several months, the cloud of ash and radioactive debris expelled into the surrounding space at considerable speeds will, in its progression, encounter slower matter, which was torn from the star during the last years of its life by instability jolts preceding its implosion. And this encounter will ignite all around the now vanished star, millions of ephemeral little suns. In the end, it's nearly 17 times the mass of our star that ends up drifting in interstellar space, forming a gigantic expanding nebula, at the center of which, where the explosion takes place, is a tiny rapidly rotating neutron star. In a way, the compressed residue of the now vanished giant star's core. All the images you are seeing on the screen are remnants of the supernova explosion. Clouds of matter initially heated to several million to billion degrees, and which were ejected by the brutal end of life of giant stars. In 1054, astronomers saw a new star appear in the sky, which remained visible even in broad daylight for several weeks before disappearing. They believed they were witnessing the birth of a distant sun. In fact, it was its death. a gravitational collapse supernova that exploded 6,500 light-years from Earth, nearly 1,000 years after the light from the explosion reached us. The remnants of this supernova, named the Crab Nebula, spread over 11 light-years wide. That's nearly 3 times the distance separating us from the nearest star to us. As extraordinary as core collapse supernovas are, they are the most common in the universe. Because all stars, whose mass is between 8 and 20 times that of our Sun, are destined to end their lives this way. It is estimated that a supernova of this type explodes every 50 years on average in a galaxy like ours. But perhaps the most astonishing thing about all this is the fact that the luminous excess of these giant stars, which, when they explode, compete for a few weeks with the brightness of a small galaxy, doesn't really reflect their full power. Because the light coming from these supernovas, which reaches us in the visible domain and shines like 1 to 2 billion suns, represents barely 1% of the energy emitted in the form of electromagnetic radiation by the cataclysm, and barely 0.01% of the total energy released by the explosion. In reality, 99% of the energy emitted is in the form of a neutrino flux that, at the moment of the star's core implosion, is released in a fraction of a second. 100 times more energy into space than our Sun will emit over its 10 billion years of existence. In terms of sheer power, that puts it into perspective. And you'll see that in the universe, we've found stars that can go even further. Thermonuclear supernovas, also known as Type 1a supernovas, are capable of emitting nearly 5 times more light than those from core collapse. And for that, they rely on one of the strangest destruction mechanisms. For the drama of these explosions to unfold, there absolutely must be 2. The story always begins in a binary system, where one of the 2 stars is a white dwarf and the other a red giant, whose outer layers, which have swelled, are slowly being vaporized by the small compact star. By siphoning and gradually devouring the gas veils of its imposing neighbor, the white dwarf becomes heavier and heavier. And when the critical threshold of 1.4 solar masses is exceeded, and while a thimble's volume of the small star contains as much matter as found in a cubic meter of rock, the collapse of the white dwarf begins. The balance between the force of gravity and the degeneracy pressure of electrons, which prevented matter from being more compacted, is abruptly broken. In just a few milliseconds, the small star is no longer here. The fact that there is initially no trace of iron in the heart, which collapses on itself, and that no layer surrounds it. As is the case in giant stars, it does not result in giving birth to an even denser block of neutrons at the center. In collapsing, the small white dwarf almost instantly triggers the fusion of almost all the elements it contains. And the star is completely pulverized by a torrent of radiation and newly created heavy atomic elements that fuse into the surrounding space. At nearly 6% of the speed of light, the torn remains of the white dwarf shine for a few weeks like 10 billion suns combined. Note that, always in a binary system, the collision between 2 white dwarfs also results in instantly triggering a thermonuclear supernova, while completely pulverizing the 2 protagonists of the drama. These phenomena of collision and vaporization, which lead to Type 1a supernovas, occur on average every 200 to 300 years in a galaxy like ours, and are among the most studied and, by far, the favorites of those who are interested in the universe on a large scale. Because thermonuclear supernovas always explode in the same way, invariably emitting the same amount of light, after exceeding a well-known critical mass. And in doing so, astronomers use them as cosmic standard candles, which allow them to measure incredibly vast distances in space. Apart from a cloud of burning matter drifting in interstellar space, thermonuclear supernovas leave nothing behind them. Invariably, the crime scene is erased within a few thousand years as the debris cloud dissipates. Hundreds of times rarer and 10 times more powerful than Type 1a supernovas, here now are the kilonovas. Here too, the drama invariably takes place in a binary system where 2 massive stars face each other. And after these 2 giants have transformed one after the other into core collapse supernovas, leaving behind them 2 extremely dense neutron stars, a strange 2-step dance begins. because this newly formed couple slowly starts to spin. For billions of years, the two neutron stars, rotating around each other, see their orbits slightly spiral. And as the system inexorably tightens, the increasingly close stars keep accelerating until the inevitable happens. The two compact stars collide and, under the violence of the impact, merge, propelling sprays of matter and radiation tens of light years around, leaving, in place of the point of contact, a single black hole. What makes kilonovas very special is that, although they emit nearly 10 times more energy than classic supernovas, the amount of visible light they emit is strangely 10 to 100 times weaker, and it fades in just a few days. This strangeness is explained by the fact that, during these encounters, only 1% of the star's mass is torn away and sent into space, at more than 60% of the speed of light, while the remaining 99% of matter ends up in the black hole. Thus, a large part of the energy is released in the form of gravitational waves, which, near and at the time of impact, ripple the fabric of space-time, creating waves that propagate through the universe at the speed of light. Over the past few decades, we have also discovered supernovas so powerful that it was deemed appropriate to create a dedicated category for them and give them a new name by dubbing them hypernovas. These space monsters, which can be seen to the edges of the observable universe, are capable of shining as bright as 100 billion suns for a few weeks, while releasing 100 to 1,000 times more energy than a core collapse supernova. And this without us yet knowing exactly how. If the mechanisms at work in hypernovas are still partly mysterious, it's because observations of these cataclysms are rare. For example, it is estimated that a star of this type explodes once every million years on average in a galaxy like ours. It is thought that these excessive supernovas originate from phenomena comparable to those at work in core collapse supernovas. Except that the stars that generate them must be much more massive, weighing in at 20 to up to 100 times the mass of the Sun. And being so heavy results, during the collapse at the center of the star, in allowing the matter plunging at full speed towards the center to impact the neutron star, without bouncing off, but continuing to crush and grind the matter to the point of transforming it into a black hole, while releasing a phenomenal amount of energy in the process in the form of powerful gamma rays. Thus, every time we uncover the presence of a black hole, it tells us a terrible story, signifying that at this exact location, a very long time ago, two small neutron stars, remnants of matter crushed by previous implosions, may have collided, unless it was a giant and extremely massive star that reached the end of its life. Impossible to know exactly how the story ended. And there, I imagine you must be thinking that the heavier a star is, the more significant the resulting explosion will be. But this is not a law of the kidneys. In fact, not all massive stars necessarily explode. We even think we have discovered that they simply disappear, without us really understanding why. Some extremely massive stars, dubbed collapse star, seem to collapse on themselves and give birth to a black hole, without even generating a supernova, as if the entire central part of the star was suddenly subtracted from the universe. In 2009, a star that shone like a million suns for several months suddenly disappeared from images without producing a supernova. One moment it was there, and the next it was gone. The giant star had disappeared. Perhaps even stranger, we've detected supernovas of a completely new kind that rely on the formation of antimatter to end their lives in the form of explosions that are among the most energetic in the universe. We believe that stars, capable of reaching masses ranging from 100 to 250 times that of our Sun, inevitably trigger what we call supernovas, by pair production of stars that produce antimatter. The puzzling principle involves the final moments of these extremely rare behemoths' lives. The extreme pressure and precise temperature at the center create hellish conditions. We'll convert the very high-energy light, which is trapped there, into pairs of positron electrons, otherwise known as matter and antimatter. And this, even before the giant star has begun to enrich its core with iron. The sudden arrival of a deluge of particle and antiparticle pairs, as a result, causes a sudden drop in the pressure that, at the center of the star, opposed the force of gravity. And the heart then suddenly contracts to the point of initiating the fusion of oxygen, and, in parallel, the matter and antimatter produced cancel each other out. The fusion reactions run wild, and in just a few seconds, barely several tens of times, the mass of our Sun begins to fuse, releasing an absolutely colossal amount of energy, which reverses the collapse of the giant star and causes it to explode, even before a compact star has had time to form at the center. These explosions do not form black holes or neutron stars. They leave behind in space only a gigantic cloud of radioactive debris, heavier than 100 suns and blood, 1,000 times brighter than those produced by ordinary supernovas, and whose brightness can last for several months or even years, and be visible practically to the borders of the observable universe. Under the conditions that currently prevail in our universe, it is thought that barely one supernova out of 100,000 draws its power from the formation of antimatter. Because stars, capable of ending their life with masses between 100 and 250 times that of our Sun, are extremely rare. In fact, the few stars heavy enough to become supernovas by pair production that have been identified to date will likely end their life much lighter than they are today. Because, deeply unstable, they are subject to continuous upheavals that constantly strip them of part of their gas veil, making them lose weight as they age. And these giant stars should therefore take their bow in hypernova or in core collapse supernova. If the most massive stars we know today struggle to maintain their mass, it's because their composition is slightly different from that of the first generations of supernova in the universe, which enriched the cosmos with new atomic elements, elements that are found in the generations of stars that followed them, and change their behavior by making them slightly more energetic and turbulent, to the point that once ignited, the most massive among them prevent the matter surrounding them from further fueling them by repelling it with strong stellar winds. Which is why, at present, the most massive stars we have been able to identify in the universe do not exceed 300 solar masses. But we are fairly certain that in the past, during the first billion years of our universe's existence, it was possible to form much more imposing giants. Giants that, made up exclusively of light atoms, could reach prodigiously enormous masses, from 300 to perhaps 1,000 times the mass of our Sun. In fact, the upper limit of the maximum mass that stars could reach during this period is still poorly defined. Did these giants of another time give rise to the most violent star explosions there have ever been, or were they too massive? Did they disappear without practically emitting any light? Imploding in a way, without any detonation or rebound phenomenon, an almost total slide into gigantic black holes? Difficult for now, to be sure. And in the hope of finding these stars from another time, astronomers scan the deep sky in search of intense stellar lights that, in an instant, would disappear. Think about it the next time you look up at the sky. It is estimated that on average, 2 to 3 supernovas of all types combined explode per century in our Milky Way. And considering that it is 100 light years in diameter, this means that the image of nearly 1,000 of these recent explosions in our galaxy are currently on their way to us. Bring it back. Given the truly gigantic size of the observable universe, it is estimated that a giant star explodes somewhere in the cosmos every second. And before we part, let me leave you with a thought. The nitrogen currently present in your DNA, the calcium that makes up your teeth, the iron in your blood, as well as the oxygen you are breathing right now. Absolutely. All these atomic elements were once at the forefront of the cataclysms we just skimmed over, because all were made inside giant stars collapsing. In this sense, taking a deep breath is a bit like inhaling the last breath of a giant star. This fascinating story I'll save for later. I hope you enjoyed exploring the core of the most massive stars in the universe. And in a future episode, we will ask ourselves from what distance these events of almost unparalleled power can be deadly. And we will look at the evidence that suggests that if the sky can't really fall on our heads, our planet's sky has already been pierced by distant debris and the energy of these explosions. To support us, it's here. For another episode, it's there.